You can go ahead. Thank you.
Thank you.
Today we have David Izquierdo-Villalba. David did his PhD at Università on semi-analytical models of massive black hole, and then moved to the University of Milano-Bicocca, where he's now working again on semi-analytical simulations, but of massive black hole binaries, which is the topic we're going to talk about today. I'm very happy he's here because, well, last year he got the Seal of Excellence of our Marie Fellowship, and this year he got the Beatrice de Pinós Fellowship, and the day after, the LISA Junior Leader Fellowship, and he accepted that one to come here to the institute, and he's actually going to start in November 15, right? November 15. So you will see him more often from fall. So thank you, welcome.
Thank you, Mark. Thank you. Thank you very much. So yeah, I'm very happy to be here, and thanks, Mark, for inviting me. So well, I mean, actually, the original title of the talk was very, very long, and yesterday in the airport I changed it and I said, what's going on with massive black hole binaries, which I think is more easier and straightforward. So, okay, let's get started. So, I mean, I like to start from the very, very beginning, let's say, because, I mean, in 1950s, I mean, thanks to the advances of radio astronomy, we were finding, well, they were finding many, many small compact objects. Okay, and they thought in principle that they were probably taking the spectrum of this object. And he found, I mean, 5 broad lines which are in principle incompatible with a stellar. The more probable thing is that it was the region, the nuclear region of a very distant and cosmological galaxy. And actually, after this, many more people started to take a spectrum of this object, and basically they were realizing that they were not only the nucleus of a galaxy, but actually a central supermassive black hole, accreting matter and radiated energy across all the wavelengths in the spectrum. And actually, right now, we know much more things about these massive black holes. Actually, we know that the mass of the black hole here correlates very well with the mass of the galaxy here, the benchmark, and so that they are very nice correlation. We also we know very, very well what is the abundance of these objects in the local universe. For instance, we know this is the black hole mass function. So here is the black hole masses, and this is the number density. So you know in which bin of masses, the number density, the number of objects divided by the common distance, the number of these objects, and seems to be pretty well constrained, let's say. And this I will tend to the 6 solar masses black holes. We can do also the same, and we know very, very well, for instance, what is called the Pulsar luminosity function, which is exactly the same, but instead of being mass, you are being luminosity. So you know how many black holes accreting matter in a bin of luminosity are in the universe at different resists. This more that is from resist 4 than to resist 0. And one thing that I like to stress is that we also know the occupation fraction. So if you take a galaxy of a given mass, you know what the typical, what is the number, what's the fraction of galaxies that contain a central supermassive black hole. Now, you can see here it's very small, but about 10 to the 10 solar masses, most of the galaxies in the universe contain a central supermassive black hole. And of course, I'm not going to say that we took a picture of, well, we took the shape of a massive black hole in the galaxy and also in the mass. So this is nice to know, but we have to contextualize everything, right? I mean, it's not nice to know that there are massive black holes, that there are, everywhere in the universe, but we have to contextualize everything, and we know that we are living in a hierarchical universe. So galaxies frequently interact, collide, and merge. And actually, if you put together this with the fact that there are many black holes in the center of the galaxies, it's not very difficult to end up with the conclusion, no, that massive black hole binaries might have formed and coalesced along the history of the universe. But now the question is, okay, how these massive black holes that in principle during the galaxy interaction are very, very far away, around kiloparsec scales, how they manage to reach sub-parsec scales and actually collide and basically merge. So right now, we don't have a clear picture of what is happening. With more or less, we know what it might be happening. So thanks with all the advances, we know that the massive black hole binaries are actually evolving in different phases, okay? And there are 3 different phases: fading phase, or dynamical friction, hardening, and gravitational wave spiral phase. And they cover, as you can see, from kiloparsec scale down to milliparsec, subparsec scale. So it's a huge dynamical range, okay? So basically, what we know is that during the first phase, the dynamical friction after the galaxy-galaxy merger, the two massive black holes are separated around 0 Pacific scales. And actually, interaction with massive black holes with the background stars in the galaxy are actually removing energy and angular momentum from the massive black hole, and basically bringing the two massive black holes closer and closer to the galactic center. Okay. Actually, the two massive black holes typically find each other at Pacific scales. Okay. But at these scales, the dynamical friction is not efficient anymore to bring the two massive black holes closer and closer, and we need to involve more processes to bring the massive black holes closer and closer to the final quadrant. And this is the case of halving phase, and basically we need interaction not with a background stars, but single stars in the galactic bulk to, again, remove energy and angular momentum from the system, and basically bring the separation of two massive black holes. And you can do exactly the same with interaction with circumbinary disks. So gas around the massive black holes are actually also able to remove energy and angular momentum through torque. Okay? And actually very interesting that at sub-parsec scales, 10 to minus 2, 10 to minus 3 parsecs, actually these mechanisms are not, are efficient, but the emission of gravitational waves is even more efficient to remove energy from the system, and they bring the emission of gravitational waves bring the two massive black holes to the final coalescence in few megayears or gigayears, depending on the masses of the massive black holes. And the most interesting thing is that during this phase, the massive black hole binaries are the most powerful sources of gravitational waves that we can find in the universe. And of course, a gravitational wave is a wave, no? And a wave can be characterized by two parameters, right? A frequency, which if you use the Kepler's law, is just basically the mass divided by the separation, no? So the ratio between the mass and the semi-major axis, okay, depending if it's eccentric binary or not, tells you what is the frequency in which the massive black hole binary will emit the gravitational waves. And on top of the frequency, we can also characterize the amplitude, which in gravitational waves is called characteristic strain. But it's very simple. Basically, the amplitude is basically just characterized by the ratio between the mass of the black hole and the luminosity distance. So how far is the black hole with respect to the observer? So very massive black hole will have a huge amplitude, but also tiny black holes very close to us will have also a very huge amplitude, okay? So now we know everything that we can imagine about gravitational waves. So we can build telescopes, let's say, interferometers to basically detect the gravitational waves coming from this massive black hole binary. So what we can do is actually build the landscape of the massive black hole binaries. So here is the frequency, 10 to the minus 10, minus 9, minus 8 Hertz, up to 10 Hertz, yes? And then this is the amplitude, random values, random amplitude in units. So the first band I want to stress is what is called Pulsar Timing Array band. And this spans between 10 to the minus 9 Hertz up to 10 to the minus 7 Hertz. And the most interesting thing here in this band is that we are going to detect massive black hole binaries above 10 to the solar masses, so they are going to be very, very massive, the most massive black hole binaries that you can find in the universe, but are rated below 1, so relatively close, let's say. Let me introduce a little bit what's a Pulsar Timing Array experiment. So it's not an interferometer per se. Basically, what you do is you have many radio telescopes in the air, okay, and you point towards pulsars, so very magnetized stars in the universe. And basically, what you do is actually track what is the time of arrival of the pulses of these pulsars, okay? So this is the time, and this is the arrival time of a pulse. So you can see that the pulsar is decelerating, but more or less irregularly. Then you build a model, which is called a timing model, because you know very well how these pulsars behave, and you can actually fit everything very well with few parameters. And then if you subtract what is the observed time of arrival with the expected time of arrival, you get what is called time residuals, okay? And of course, if we live in a perfect universe, this amplitude of the residuals is basically telling you if it's passing or not a gravitational wave between us and the massive black hole binaries. So if a gravitational wave passes between us and the pulsar, given that it stretches and compresses space-time, the time of arrival will be delayed or anticipated with respect to the expectation. No? So everything, all this delay or anticipation will be basically encoded in the amplitude of this time of arrival. Okay? So right now there are, I think, 6 big collaborations, basically taking radio telescopes in the Earth and basically monitoring the time of arrival of many different pulsars. And actually, there are, for instance, the European Pulsar Timing Array collaboration, the North American Pulsar Timing Array, which is nanograph, Australian, which is PTA, Chinese, PTA, the NIRCAP, and PTA, or all of them are basically under the umbrella of International Pulsar Timing Array collaboration. And what's happening right now? So, well, Pulsar Timing Arrays can actually detect single massive black hole binaries, the gravitational waves coming from single objects in the universe, but also detect what is called the stochastic gravitational wave background. So it's the incoherent superposition of all the gravitational wave signals emitted by the population of massive black hole binaries. And actually, 2 years ago, we, because I am also part of the collaborations, found strong evidences, not a detection yet, but a strong evidence of the existence of a gravitational wave background whose amplitude is between 2 up to 3, 10 to minus 15. This number doesn't tell you right now anything, but later I will go on in this number. And then we have the other band, which is between 10 to minus 4 up to 10 to minus 1 Hertz, okay? And it's basically the LISA band, which is basically the LISA space gravitational wave detector. And here is going to be very complementary, because instead of detecting the most massive black hole binaries in the universe, we're going to see the lightest massive black hole binaries in the universe, between 10 to the 4 up to 10 to the 7 solar masses, but in this time, up to cosmological distances, up to redshift 20, so where the very first massive black holes are actually formed. Few words about LISA. LISA is basically a constellation. It's basically built with 3 telescopes, interferometers. Basically, it's an heliocentric orbit around the sun. And each basically of these 3 to detect gravitational. It will do, because it's going to be done in 2030, 25, 35. Let's hope. So basically use a time delay interferometry. It's not the usual interferometry like LIGO does, but well, it's something different because the separation between the 3 satellites is very, very large. And in this case, LISA space-based gravitational detector is going to see only single massive black holes, not stochastic gravitational background, but only single massive black holes. Okay, now you know everything about gravitational waves and massive black hole binaries. Now the question is, why they are so interesting, why we are investing time and resources to detect this massive black hole binary. Well, the very first thing is that we can constrain galaxy formation and massive black hole or binary massive black hole formation models. For instance, with Pulsar Timing Array, the stochastic gravitational wave background is extremely correlated with the number of massive black hole binaries that we can find in the close-by universe. Whereas for LISA, the number of detections that we will see are extremely correlated with the formation scenario of the first massive black holes in the universe. But also we can do multi-messenger astronomy, which is something very, very new. And basically, it's very simple conceptually, because first, you have to detect the gravitational wave coming from the massive black hole binary. And with this detection, you can actually determine the luminosity distance, because if you remember, the amplitude, the characteristic strain of a massive black hole binary is just correlated with the mass and also the luminosity distance. So you can confirm very well the luminosity distance. But if you detect also the massive black hole binaries in the electromagnetic spectrum, you can constrain the redshift. And you know that the luminosity distance and redshift are correlated with cosmological parameters. So you have the measurement of 2 different quantities related among themselves. You can start constraining what cosmological parameters such as the Hubble constant. But there are issues. I mean, this is not so simple, right? Because the recent values of Pulsar Timing Array collaborations have reported this amplitude of 2, 3, 10 to minus 15 seems to put in troubles what we know about galaxy formation and massive black hole binary formation scenarios. I will speak more about this. And finally, for multi-messenger astronomy, the detection of the electromagnetic emission coming from the massive black hole binary or the galaxies from their side is extremely challenging. So in this basically seminar, this talk, I want to just speak with you about what galaxy formation models can tell us about the recent detection evidences of the stochastic gravitational wave background seen by Pulsar Timing Array. And the second part is how feasible is the performing multi-messenger astronomy with massive black hole binaries that LISA or Pulsar Timing Array will unveil in the next 10, 20 years. So in order to address all these, okay, I need to have, many different ingredients because, first, we need galaxy formation model. Well, we need galaxy populations because the massive black holes and galaxies are very correlated, as I told you. So we need to have an accurate galaxy population. The second ingredient to basically answer these two things is that we need accurate massive black hole populations, no? Because we need to understand what is massive black hole binaries, but massive black hole binaries are a subsample of massive black holes. No? And finally, we need accurate massive black hole binary evolution, dynamical evolution models to basically transform massive black hole binaries to massive black holes, to massive black holes. So in order to fulfill all these ingredients to answer these two questions, we can use galaxy formation models. In particular, I want to speak about L-Galaxies, a semi-analytical model for galaxy formation model. So I don't know how familiar you are with this terminology, but semi-analytical models are basically computational tools that basically take the merger history of dark matter objects, okay, across cosmic history, and basically they paint galaxies on top of them to understand how galaxies form and evolve, interact, and actually how massive black holes form and evolve. And for instance, the galaxy semi-analytical model, this merger history of dark matter halos are taken from different M-body simulations, in particular the very well-known Millennium simulations, but also, for instance, what is the TNG dark matter only simulations. What about the physics that L-Galaxy includes to understand the formation and evolution of massive black holes, massive black hole binaries, and galaxies? Well, our galaxy includes many different in situ processes, such as star formation processes, supernova feedback, alien feedback, but also environmental processes, which are very, very important, such as galaxy tidal disruption, gas stripping, so on and so forth. And with this, actually, L-Galaxies has shown to be very, very accurate and very precise to reproduce what we see at least up to redshift 3 in the universe. For instance, this is the stellar mass function, the number density of galaxies with a given stellar mass beam as a function of redshift, from redshift 3 up to redshift 3. So the blue dots are actually the data, and the the red line are the constraints from the galaxies. You can see it's very, very precise in reproducing this quantity. But not only that, the star formation rate density, so how many stars galaxies form across cosmic history, also the mass metallicity relation, how metallic are the galaxies, or the most interesting thing that many semi-analytical models and galaxy formation models fail in the fraction of passive galaxies at different redshifts. Okay, so L-Galaxies have a complete module to understand physics on top of the dark matter simulation. But what about massive black holes? Well, it includes a very sophisticated seeding model in which we can track the formation of 3 runaway stellar layers and direct collapse. So different flavors in which massive black holes can form at different history of the universe. And for instance, we are able to characterize the typical birthplaces of the first massive black holes at very, very early times in the universe. So for instance, this is a projected map of the galaxies around that, for instance, a newly born black hole formed throughout this direct collapse black hole scenario, which we can see later, or the runaway stellar layer scenario. So you can see that the environments are very, very different. And there are very multi-flavor scenarios of forming massive black holes in the very early universe. It also includes a different growth model, in particular Eddington, Super Eddington, and Super Eddington. So different channels of massive of growth of massive black holes through gas accretion. And actually, it grows mainly, these channels of growth are basically triggered after galaxy merger. So the two galaxies are actually interacting. And part of the cold gas actually can lose angular momentum and flow to the center of the galaxy where the massive black hole is, and actually give matter to the massive black hole and make it grow. Also includes secular processes, such as ordered processes in which massive black holes can accrete matter. So for instance, the formation of a spiral arms, or for instance, the bar formation can actually also trigger inflows of gas to the center of the galaxy and also trigger the growth of massive black holes through accretion. Also includes a model for the spin evolution because the massive black holes can be characterized by mass, but also by spin, and we have to track also the speed evolution of these massive black holes. And in particular, for instance, this is the prediction of the semi-analytical model. So this is a different redshift from redshift 1 and to redshift 4. What is the typical spin parameter of massive black holes at different masses? So you can see that most of the massive black holes in the 10 to the 8 a very high redshift are highly spinning. So they are spinning very, very fast. But also up to 10 to the 8 solar masses, the spins tend to be, the massive black holes tend to spin less, let's say. And also there is a redshift evolution. High redshift massive black holes tend to be more highly spinning than low redshift massive black holes. So we have prediction from the semi-analytical movement. And actually, when you compare with redshift zero observation from few massive black holes that we have in the spin, you can see that the model is pretty well constraining or reproducing what we see in the X-ray selected agents. Of course, we include also agent filter because it's very important, because the accretion of matter onto the massive black hole can also produce energy, okay, and this energy can actually hit the the close by gas and actually can halt or stop the formation of stars in the galaxy. And these are the predictions. If you put together with galaxies and massive black holes, the predicted population of massive black holes that we have in the galaxies in the analytical model. So this is the black hole mass function, and this is the luminosity function. So the black hole mass function, as I told you, tells you what's the abundance of massive black holes with different masses. And again, the points here are the observations, and the blue line are the predictions. So the same analytical model is predicting more or less okay, but it's the number of the abundance of massive black holes in the local universe. But also what we see here is the luminosity function. So we also predict pretty well what is the accretion of massive black holes across cosmic systems. So this is the luminosity function at 4, 3, 2, 1, 0.550. The points are the observations, and the black line are the predictions from the semi-analytical model. So we correctly reproduce the number density of massive black holes that are actually growing through gas accretion. And the most important thing is also that the galaxies include a unique model to track massive black hole binary dynamics on the fly, on why galaxies and massive black holes are evolving. Phase. So for the fading, it's happening after the galaxy-galaxy merger. And basically, we put a time clock in which the massive black hole takes from the galaxy-galaxy merger to reach the center of the galaxy. And it's given by the dynamical friction from Santa Seca, particularized to isothermal sphere. Just for simplification. Then for the hardening phase, we track also the semi-major axis and also the eccentricity. So we know what the mass of the black hole, the spin, but also what is the separation between the two massive black holes and what is the eccentricity. And finally, we also include tripods. Basically, a massive black hole binary can be there in the galaxy, but actually into the galaxy merge with this galaxy, and then you deposit a new black hole in the galaxy. So now you have three black holes in the center. So we also model this tripod interaction in the semi-analytical model. And also, the most important thing I believe is the gas accretion. We also model how massive black hole binaries accrete when they are in the binary, okay? So typically there is a triple binary disk, and then there are two mini disks around the two massive black holes that fuel gas onto the massive black holes and give rise to electromagnetic emission, which is going to be very important now for this multi-messenger astronomy. And also, finally, L-Galaxies has also a module that will transform the moving boxes of the simulations of the embodied simulation into a light point. So now we can place galaxies not only around, across redshift, but also across the right ascension and declination. So we can actually make, let's say, mock universes from the semi-analytical model. So we can compare one-to-one between predictions and simulation. Observations and simulation. So for instance, this is an example. Takes the function of the redshift and the right ascension. So you can see here a black hole. So each black hole is a galaxy. You can see it's distributed across classes, filaments, and so forth. So the lattice scale structure is very well described by these light-poles and in this semi-analytical model. Okay, so now we have all the ingredients required to understand, to try to keep light on the galaxy formation model about our PTAs and about multimessenger astronomy. So now we are ready to start exploring what galaxy formation model tells us about Pulsar Timing Array and what is the expectation of multimessenger astronomy with massive black hole binaries. So let's get started with the first part, massive black hole binaries in PTAs and what galaxy formation model can tell us. So as I told you, Pulsar Timing Array is going to detect single massive black holes, but also the stochastic gravitational background. And the stochastic gravitational background is typically characterized by an amplitude and a frequency dependence. Okay? And what we see from Pulsar Timing Arrays Actually, these are the papers in which they show the evidences of the existence of the stochastic gravitational background. These are the typical values that they found is between 2, 3, 10 to the minus 15. Okay? This is what they found. Perfect. But if you go to the literature, the predictions that we were making before these observations took place, if you take, for instance, the observed galaxy-galaxy merger rates, and you put some recipes, let's say, to understand what happens on massive black holes after galaxy-galaxy merger, what you were finding is between open 1 up to 1, 10 to the minus 16. So very, very, very far away from what we see in observations, okay? So now here comes the question, can galaxy formation models, I mean, if you model evolution of galaxies, massive black holes, and massive black hole binaries together, can actually reconcile what we see in observation, what theoretical models were saying before all these Pulsar Timing Array collaborations were actually taking data and publishing these results. So, well, what I did is basically running a galaxy model. I generate a population of massive black holes across cosmic history. And what I did is selecting the galaxies with massive black hole binaries, and compute what is the prediction of the stochastic gravitational background. So basically, I took this equation and I computed what is A and what is F. So what I found, the amplitude predicted by L-Galaxies semi-analytical model is 1.2 10 to the minus 15. So again, we are on travels, no? I mean, if you compare observations with theoretical models, L-Galaxies, which is semi-analytical models of galaxy evolution, tend to be more closer to what we see in theoretical models. So we have a really big issue. Galaxy formation models cannot predict and explain what we see in Pulsar Timing Array collaborations. So now the question is, can we change something in galaxies, for instance, the dynamical evolution of massive black holes, the growth of massive black holes, so we can change something that we put in the semi-analytical model to basically move this amplitude closer and closer to what we see in Pulsar Timing Arrays. So this is what I did. Well, actually, we did in the European Pulsar Timing Array collaboration. And this is the fiducial model, okay? And this shade area is 2, 3, 10 to the minus 16, okay? So what you see is, okay, the model fails. It cannot reproduce what we see in Pulsar Timing Array. But what about if we modify the dynamics? Maybe we make the massive black hole binaries to grow faster, to evolve faster or slower. So what we found is that the dynamics basically doesn't move at all. What is the prediction from the stochastic gravitational background? And this is because the evolution of these massive black hole binaries that Pulsar Timing Array are seeing, they are evolving very, very fast already. So the dynamics really doesn't play a role in the stochastic gravitational background. But what happens, we modify the growth of massive black holes. So now, instead of assuming a given efficiency in which the massive black holes can accrete matter, what about if we put a little bit more gas? So maybe the massive black holes are more efficient than expected in accreting matter, okay? So what we found is that if you allow progressively more and more efficient massive black holes, so matter, basically massive black holes consume more efficient matter, okay? What we see is that the massive black holes are more massive. And given that if you remember the amplitude is correlated with the mass, they are louder, and you can actually reconcile what we see in Pulsar Timing Arrays. So what we need is massive black holes more massive, let's say, okay, to reconcile what we know from galaxy evolution with what we are seeing with galaxy formation model. So now the question is, well, this is what I say, is the question is, are these models that are compatible now with Pulsar Timing Arrays, with massive black hole binaries, still in agreement what we see about massive black holes, single massive black holes? Because if you remember, L-Galaxies were reproducing the general population of single massive black holes. But now that we force this to match the stochastic gravitational background, are the single population of massive black holes still compatible as we see in electromagnetic emission? So the answer is no. So this is the black hole mass function, the number density of massive black holes at different beams of massive. So the data again are the square inside circles and the shade area. And the fiducial model, which was producing this 1.2 10 to the minus 15, it was very well constraining what we were seeing in the local universe. But now if you force the model to reproduce what we see in the massive black hole binary band, you can see that we are failing a lot in producing the core population of massive black holes. We need to overpredict the number density of massive black holes in the local universe to give an answer about what Pulsar Timing Array are seeing. And the same for the luminosity function. We need, this again, the data. The black line is the fiducial model, which was produced in 1.2 10 to minus 15, and the orange is 10 to the 3 10 to minus 15, compatible with Pulsar timing. So you see, we need to also predict the number density of accreting massive black holes to reproduce what Pulsar Timing Array is telling us, okay? So it still is an open question. I mean, the signal that we saw in this Pulsar Timing Array band, let's say, is too loud, it's surprisingly loud, much more than expected. It's very difficult to reconcile what we know from massive black holes and massive black hole binaries, okay, to what we are seeing right now in the gravitational spectrum. But the good thing is that the gravitational wave spectra, let's say, data is finally providing strong constraints about galaxy formation. Okay, so let's move to the second topic: is how feasible is multi-messenger astronomy with basically Pulsar Timing Array and LISA, massive black hole binaries. So let's get started again. So again, let me summarize again. If you detect the massive black hole binaries in the gravitational wave, you can constantly move the distance. If you detect the massive black hole binaries in the electromagnetic spectrum, you can constrain the redshift, so you can do this multi-messenger astronomy constraining cosmological parameters. But why is so challenging, no? As I was posting before? Because it's sky localization, okay? So once you detect the gravitational waves, the detector can give you a more or less a region in the sky in which you should look for the detection of the massive black hole binary. So it doesn't give you a single point, but an area, okay? So for instance, in LISA, okay, the other detector, the massive black hole binary can be seen from months up to hours, even at merger, okay? And basically the sky localization is fast. You can see that varies a lot from 100 square degrees at months before the merger when you detect the massive black hole binary, up to 1 square degree at merger. So you can see that varies a lot, but it's always above 1. Array, you don't see the massive black hole. You don't see a volume in the binary, but depends on the signal to noise ratio. So for a massive black hole binary, for instance, detected with very high signal to noise ratio, it's very, very clear. The detection is very clear. You can constrain more or less around 100 square degrees. It's huge. Even the loudest massive black hole binaries in Pulsar Timing Array are going to be constrained in the sky in that huge area. Okay? So this is a summary. Pulsar Timing Array is the typical sky localization, and this is for this typical sky localization. So if you take the two smaller values, and for instance, you have an idea of this is the ultra deep field of Hubble, which is around this 0.1 square degree. You can see that there are a huge number of galaxies there. So how feasible is that once we detect the gravitational waves, if we look for a galaxy or an AGN in this patch of the sky, we will find unequivocally the host or the AGN which is hosting the massive black hole binary. So for that reason, it's also difficult. So yeah, so the question is how doable is multi-messenger astronomy and how feasible will be the multi-messenger astronomy with massive black hole binaries. So what I will explain here is basically how feasible is doing multi-messenger astronomy when you have Pulsar Timing Array massive black hole binaries and LSST, okay, so optical detection. And with LISA, how feasible is multi-messenger astronomy if you link LISA and Athena, which is an X-ray observatory, okay? So let's start first with LISA. So what I did is very simple to study this thing. So what I did is taking L-Galaxies semi-analytical model and building a mock sky. Okay, again, this is the redshift, linear attention. Each point here is a galaxy from redshift 0 to redshift 3. And what I did is basically selecting massive black hole binaries in this virtual unit. Then once I have these massive black hole binaries, I compute which ones are detected by LISA. And after this, I assign to each one a sky localization. Okay? And this is the outcome. So this is the Ryan extension definition for a massive black hole binary in red here. The upper one is 10 to the 6 solar masses at redshift 2, and 10 to the 5 at redshift 4.5. Both of them are at merger. So the base case scenario of merger, where the sky localization is smaller. And this is the field. You can see just by eye the number of galaxies in which you have to look and perform electromagnetic observation is huge. Extremely high, the number of galaxies there. How much? Well, this is a summary. This is as a function of the redshift when the massive black hole banner is detected. What's the number of galaxies within the sky localization? And this 10 hours before the merger, in blue, red, black 1 hour, and red at merger. So of course, given that the sky localization was improving when the massive black hole was closer and closer to merger, the number of galaxies within the sky localization is smaller, just because the area is small. But in the best case scenario, you can see that the number of galaxies within the sky localization area can be hundreds up to thousands of galaxies. Huge. Imagine just doing a follow-up of 10 to the 4 galaxies, 10 to the 3 galaxies. Incredibly challenging. In the best case scenario, which is low redshift, you can see that the galaxies can vary between 20, 50, up to 100. So it still is very, very large. So now here comes Athena, which is this X-ray observatory, which is, well, what it was Athena back then, because now it's degraded, whatever. So how Athena can help you on this? So if you only select, for instance, AGNs, so if we assume that all these massive black hole banners will be powering AGNs, will Athena reduce the number of galaxies that we have to do this follow-up, electromagnetic follow-up? So again, this is this is the sky localization again of the same binaries. Here is when we don't put any cut. And here then we only select basically AGNs compatible with 10 to the 5, 10 to the 6 massive black hole binaries in the sky. So you can see that the number of candidates can be reduced a lot. So here you see, it's populated with a lot of galaxies. Here there are few. And here is a very, very nice case in which all these galaxies, the number of candidates is reduced just to the true host and the candidate. How much? Well, this is the same as a function of redshift. What is the number of candidates compatible with an X-ray emission seen by Athena? And again, there is the typical dependence with the observing time. So 10 hours before the merger is going to be very high. But at merger, you can see a very low redshift. So there are 1, 2, 3 galaxies. So performing multimessenger astronomy with LISA and Athena at very low redshift will be very, very, very efficient. Actually, you can constrain it very well. So the sweet spot for multimessenger astronomy between LISA and, for instance, Athena, that you can do the same for the observatory, is a low redshift and time before the merger below 1 hour. So there are hopes to perform multimessenger astronomy with LISA. Cool. What about Pulsar Timing Array? Because LISA will, I didn't tell you, but LISA will fly in 2035 around. So there's still a lot of time. But Pulsar Timing Array, actually, they are really taking data and really constraining the population of massive black hole binaries. So right now, we can actually combine Pulsar Timing Arrays with LSST, optical detections. So what I did in order to understand how feasible is performing this multimessenger astronomy between Pulsar Timing Arrays and optical observatories such as LSST, what I did is taking the galaxies and in this time creating even a bigger volume, a full sky light one. Okay, so this is the Rayleigh extension, full sky light one, all the sky, and this is the redshift. Okay, here I just started the redshift of 0.3 because of what it was too messy. And again, each point here is a galaxy, there are some clusters, some filaments, so on and so forth. And again, what I did is which Pulsar Timing Arrays we are going to use? Well, we said we are going to use what is SKA, okay? So basically 30 years of data, radio data, and 200 pulsars, okay? And this is the distribution of pulsars that we will use to look for massive black hole binaries in Pulsar Timing Array. And then we perform basically an analysis to understand which population of massive black hole, which massive black hole binaries will be seen by Pulsar Timing Array, in particular this one. And then we started to constrain the sky localization. So for instance, this is a very nice example in which here is just the pulsar. And then this sky localization area, you can see it's really huge. For a massive black hole binary of 10 to the 8 solar masses, seen by this Pulsar Timing Array, we can see that to a ratio of 6. So you can see that it's huge sky localization. But okay, let's try how feasible it is to perform this multimessenger astronomy. So what we found is that Pulsar Timing Array in 30 years will see around 30 single sources, single massive black hole binaries, which is pretty much a lot, to be honest. And this is going to be the signal to neutrino ratio, how clear is going to be the detection, let's say. So most of them are going to be very, very low, between 5 to 25, well, 5 to 15, okay? And the rest, there's a tail of massive black hole binaries that will be seen with very, very, very few signal communication. They are going to be extremely clear. As soon as you point your telescope, you will have a clear detection. Of course, the typical masses are going to be around 29 solar mass, so even bigger, as I said before. So they are going to be extremely, extremely massive. And the rest, as I told you, is going to be below redshift 1. What's the typical host? So, well, here is the distribution of stellar masses. So you can see that most of them, of the massive black hole binaries, will be placed in galaxies around 10 to the 11, 10 to 11.5, so the biggest galaxies in the universe. And what's the star formation rate? How active are these galaxies in forming a star? Well, there's a cumulative distribution function of the distribution. Around 50 of them can be active star-forming galaxies, but most of them are going to be quiet, quench galaxies, dead galaxies. So are going to be very massive galaxies and very dead galaxies, okay? No star formation. So what about the photometry? Okay, now we are starting to approach the multi-messenger. We are going to see these massive black hole binaries and these galaxies in the LST survey. So this is again the cumulative distribution function. Well, this is the magnitude and the cumulative distribution function of the massive black hole binaries. So if they have a magnitude, it means that they are active and they are active in matter. So they can be as an AGN. If there are no magnitude, they are not active in matter, so they are not AGN. So you can see here, I mean, these lines are the limited magnitude of the survey. So below here, well, higher than this value, you don't see them. They are basically inexistent. So you can see that only 10, 15% of them are going to be seen as an AGN. So this plot is telling you very clear that if you want to perform multi-messenger astronomy with Pulsar Timing Array massive black hole binaries, don't look for AGNs because very, very few of them are actually active in matter. So they are no IGNs, okay? Okay, so if we cannot look for AGNs, let's look for the galaxies, no, at least. So this is again the cumulative distribution function of the galaxies, the magnitude of the galaxies. And again, these lines are the limiting magnitude of the survey. Above this, you don't see anything. And you can see that at least all the galaxies in which these massive black hole binaries are placed are going to be seen by LSST. At LISA, no? Which was seeing AGNs. Okay, but what's the number of galaxies within the sky localization? Okay, now we know galaxies. Okay, how many of galaxies are within the sky localization? For instance, if you detect a massive black hole binary with a signal to noise ratio of around 10, the number of galaxies similar to the Pulsar Timing Array 1 are actually 100, 200, even higher. But if you go to very, very high signal to noise ratio, very, very clear detection, you can see that the sky localization is diminishing, so the number of galaxies only 10. Very, very good for follow-ups, electromagnetic follow-ups. But there is an issue. If you remember, this is the signal to noise ratio distribution of the detected sources. So the vast majority are around 10 to the 5 to 15. So these are the cases in which we will be speaking about. So the number of galaxies we see in the typical detection of single sources by Pulsar Timing Array are going to be 10 to the 3 up to 100. So still many, I mean, a lot of galaxies. So it's going to be extremely challenging for Pulsar Timing Array to multimesh. So the question is, can we use, for instance, all the information of the galaxy to basically discard the galaxies which are not really the possible hosts and only focus on the real ones? So for instance, what we thought is performing, for instance, color diagram, okay? And understand if the galaxies were placed, the galaxies hosting massive black hole binaries detected by Pulsar Timing Array were actually populating specific regions of the color diagram. For instance, this is the distribution, well, let's move here, color delta. So the red points are the galaxies in which we will find a massive black hole binary detected by Pulsar Timing Array. And the contours are the galaxies within the sky localization area. So you can see that the points and the contours are clearly overlapping. So we cannot use any extra information from the optical, basically magnitude that LSST is giving us to basically separate between the true host, red, and the fake host, which are the blue ones. So basically, no, we cannot use any extra information to constrain the galaxy in which the massive black hole binary is placed. So this is telling you that pulsar timing arrays are going to have a lot of difficulties to perform multi-messenger astronomy. So yeah, so the conclusion from this part is just LISA and Athena are going to be a very good. It was because now Athena doesn't like it was before, but it will be a very good synergy to detect what massive black hole binary. So we will perform multi-messenger astronomy very well with LISA and Athena. What about pulsar timing array? Well, if we use LSST, for instance, it's going to be very complicated. They are not going to be AGNs, they are going to be only galaxies, normal galaxies, but they are not going to be particular galaxies. They are going to be normal, massive, dead galaxies, which are going to be very difficult to disentangle between the true ones and the true host and the fake host. So, yeah, with this, I hope I convinced you about these two topics, galaxy formations. Well, gravitational wave detections are finally giving constraints on galaxy formation model, and it's very nice. But for the very first time in the history, we are placing another constraint in galaxy formation model, not only coming from electromagnetic survey. And finally, how feasible is to perform multi-messenger astronomy to, for instance, constrain cosmological parameters? Well, there are cases in which, for instance, LISA is going to be very efficient and low redshift, but pulsar timing arrays, which are providing now data, are going to have a lot of challenges to perform this multi-messenger astronomy and help in the constrained cosmological parameters. So that's everything. Thank you. Okay, that is my talk. So we have time for questions.
Thank you. Very nice talk. I'm not in the field of what nice. Well, I have a question on both of the parts. Sure. The first one, when you compare the amplitude of the yeah. So I have two questions here. The first thing is, I think your uncertainty on your model comes from many things. So I'm very surprised by how you show. Basically, you tell me you think your model is better than 1 order of magnitude, considering all the uncertainties on dark matter models for the formation of large structures, the evolution of this all the way down to the project. Is this really paid, and is this really
No, that's a good question though, because here we freeze everything from galaxy formation model and dark matter. What we only vary is the accretion of massive black holes and the dynamics. So these are the uncertainties coming from these only two channels. Of course, if you add all other things, the error bar will be huge. Huge. Yeah.
Thank you. I feel
you need to believe.
Back to the uncertainty, but
sure.
The question is, you only assume uncertainties on your galaxy, but I suspect the model that is used to measure this amplitude, so basically the energy of dark matter from fitting the pulsar, must have also quite a bit of uncertainty. Because these deviations from the smooth curve that you interpret as coming from gravitational waves may also come from intrinsic pulsar physics.
Sure. Because I didn't speak about this, but when they compute these residuals, basically how different is your fitting model with respect to what here, basically, here you assume also all these uncertainties. And actually, these are the biggest uncertainties on this model. For instance, this is called the red noise, right, of the pulsar. So, for instance, if it's in a binary, it's not only one single pulsar. Also, you have to model this. Also, for instance, how the pulse, for instance, when it reaches the solar system, it also passes through a lot of ionized bubbles and these things. So, also, this varies a lot, the time of arrival, so on and so forth. So, what you do is fitting everything to what red noise models, so basically a power load. But this also introduces a lot of uncertainties here. So for that reason, we should take with a grain of salt what pulsar timing array are seeing right now. Because it seems that it's very high, but it's also, the amplitude is very high, but also the spectrum is a little bit convoluted, everything. So right now we in the field, I think we are over-interpreting the results. So we should basically take into account that they are preliminary results, they are not detections, it's just an evidence. And we should model, for instance, all these uncertainties in Pulsar timing arrays, all this red noise, white noise, so on and so forth. And also we should take into account that, galaxy formations have intrinsically a lot of uncertainties. So, of course, this is assuming that all the gravitational wave signal that we are seeing in Pulsar timing arrays are coming from massive black hole binaries. Exactly. Can be from, this exotic, cosmological assumptions like, inflation, dark matter, also can produce also this type of gravitational waves. In the European Pulsar timing array interpretation paper, we also speak about this and the implication that we have, for instance, in dark matter, or this inflation, or this, but yeah, you should also take into account that we assume that everything is massive black hole binaries, but maybe only 5% is massive black hole binaries and the 95%. So yeah.
Yes, yes, yeah, to know this question, I only have one. So, for the arithmetic from the past in LISA, so, we know very little, right, about what can be the quantum passes themselves, and what the mechanism that produce the, X-ray, for instance, in the case of now. So what is the status on this? What are you assuming?
Yeah, for right now, we are assuming, in the model, what is called the preferential accretion. Okay, so basically you have a massive black hole binary, and if you run an hydrodynamic simulation, so around, with gas and so on and so forth, you see if the massive black hole binary is very unequal, the tiny massive black hole, the small massive black hole tends to be closer to the circumbinary disk. Okay, so I mean that is closer to the circumbinary disk is able to accrete more. So at the end of the day, after few giga years, the two massive black holes become an equal mass system. Okay, so this is called the preferential accretion. The secondary accretes more than the primary mass system. So this is what we are assuming right now. And basically, the accretion is triggered after galaxy-galaxy merger or secular processes. So it's very, very, very basic assumption right now. But yeah, for instance, there are some papers in which they claim that, for instance, in X-rays, let me go here. So here is the circumbinary disk, and then you have the two mini disks. And then most of the radiation in X-ray is coming from the mini disk because they are closer to the massive black hole, so they are hot and also be emitting X-rays. So there are some papers saying that, during the merger, you will see an AGN, okay, an X-ray AGN, but at merger, the two emit emission in the X-rays. So you can also explore for variable massive black hole binary, massive black holes in X-rays, for instance, to even constrain, to basically diminish even further these numbers. Yeah. So if you look for variable AGNs in X-rays, so one AGN that appears, normal, then it vanishes, and then after a few days, it rises again, could be a good smoking gun for a massive black hole binary. Sorry? Yeah, that's the problem. That's another problem. Yeah, but here they will vanish totally because because the mini disks disappear completely because basically they are blown away because the two massive black holes are so close. So basically they're blown away all the gas in the mini disk, so they don't emit any more X-rays. And then all the gas after the merger flows again to the center. You have a black hole. But of course, this intrinsic variability of AGN is also a big issue, and you can most of the candidates of massive black hole binaries through variability studies are candidates. Because it's very difficult to say, okay, this is a true variability because a massive black hole binary, because the periodicity of the massive black hole binary, or because actually it's just a random, basically, random modulation of the basically accretion D, so on and so forth. So yeah, all the candidates that we have now about massive black hole binaries through variability studies are just candidates, and probably most of them are fake because intrinsic variability.
I have a comment and a question. The comment is about the PTA, what we discussed at the beginning. So if the measurements are not really trustworthy or real measurements, then maybe there's no point in forcing the models to go that range of 2 to 3, because maybe with more reliable measurements, the number will increase to 1, right? So maybe the models are okay.
Exactly. So this is the overpredict interpretation of what we're speaking, right? I think now there are a lot of overpredict interpretation. of the signal of Pulsar Timing Arrays. So I think we should wait until the next releases of Pulsar Timing Arrays, because they will improve, of course, the timing models or the noise that they have. And probably, that's my impression, it will fall, because most of the constraint in the signal is just coming from one frequency group, and you have 10 frequency groups. So, I mean, if you improve a lot your data, the constraints will actually, for sure, change something.
My question was about the SKA.
Yes.
So, yeah, I didn't really understand what's the input there. So I think that was pretty clear, but we can get it.
Yeah, for SKA is basically just, you mean like what's the input in?
How does it help?
That's the point, nothing. I mean, nothing help. The point is that it's clear that, I mean, what I show here is like, if you, for instance, because Pulsar Timing Arrays will be seen in the full sky. Well, massive black hole binaries will appear in the full sky, right? So if you want to do multi-messenger astronomy from the Earth, you should have a very big wide sample, right? And right now, what we thought is that LSST will be the perfect one. Also, it's very deep, right, in magnitude. So we said, okay, under the assumption, okay, that LSST will see most of the sky. We can start performing multi-messenger astronomy with this. And the answer is no. I mean, you should look for normal galaxies, not optical AGNs. And unfortunately, there are no different galaxies in the optical spectrum. So LSST is not really given good constraints on the multi-messenger astronomy with Pulsar Timing Array. Of course, for the cases in which the massive black hole binary is detected with signal ratio around 40, the number of galaxies can be just 2 in the optical. So in these cases, are going to be it's going to be feasible, the multi-messenger, but it's just 1 in 1 million cases. So.
I asked for SKA. You mentioned.
I'm sorry, SKA, LSST, okay. No, SKA is to, sorry. SKA is just to generate the population of particles. So SKA is going to do the timing array, timing model. It's going to be the detector, let's say, of gravitational waves.
How long do you have to wait? Because in the beta stack still, right?
Yes. So for instance, the predictions to detect one massive black hole binary with current data of Pulsar Timing Array, very low, probably 1, at most 2. Of course, there are these are the continuous gravitational sources, okay, single sources. There are studies that they are doing this with Pulsar Timing Arrays. There are some, it seems that there is one hotspot around Virgo cluster, but it's not clear if there is a single sources in the Virgo, a massive black hole binary in the Virgo cluster. So we should wait at least for 10 years or 13 years. It would be nice.
I have a question. So now that we have destroyed the PTA, can we go to LISA?
Let's destroy LISA.
When you were showing the X-ray detections, that you said there are only 2 objects.
Yeah.
So I'm also outside from the thing, but my understanding is that you want the electromagnetic observations, so spectroscopy to define the redshift. But here you are already doing some separation between different redshifts, right? But you don't know this as a priori.
Exactly.
So you will have all the sources that have detections of X-rays that you will have to still.
No, that's a good question, because LISA, on top of constrain the ray extension and declination, can also constrain the luminosity. Okay. You have a priori actually in the width. PTA doesn't, because to constrain the luminosity distance, you need the variation of the frequency. So basically the spiral phase. You should see the spiral phase, not only the merger, but also the spiral. LISA can see this, but Pulsar Timing Array no. So for that reason, with Pulsar Timing Array, you have a huge area, but also a huge volume.
So with LISA, you can still make some.
Do tomographic, let's say, yeah, exactly.
Okay, I have a follow-up question. I don't know, Athena, can you maybe resolve all these groups with Athena?
Yes. Yes.
How it went?
Yeah, I would have. Yeah.
Because I think you are looking into something for resolution, and I'm sure you guys have thought about it. Did you investigate what kind of signature you would expect from radio interference?
That's a good question. We didn't. Because we didn't. We only took. Yeah, that's a good point. Yeah.
I have no idea whether there will be an expected. Well, I
Yeah.
suspect there might.
Yeah, that's a good question. We never thought about, well, at least me, I never thought about doing this with radio observations. But yeah, I mean, it could be a good approach to, because it would be nice to do this, but not only one band X-ray, but also optical X-ray, radio. So all the, I mean, because we need to, I mean, okay, this is going to happen in 20 years, 10 years, 15 years. But we should start getting ready now to perform this, because as you saw, I mean, it's very challenging. I mean, because, okay, there are cases in which, okay, we can see the true host, but there are cases in which we have to disentangle between many sources. So we have to start, I mean, building up very good strategies, to perform this multi-machine astronomy, because probably, okay, I mean, if we see one binary here, but if imagine that now the population of massive black hole bodies are predominantly merged in a redshift 2, then the bulk of the population is here and there are no influence. So we can use all this part. No? So we should start getting ready to perform this multi-messenger exploration. And I think this is something that, I mean, very few people more people started to realize about this. So there are many more works on this multi-messenger, different observations in electromagnetic spectrum to follow up in gravitational waves.
Thanks, David.
Thank you.
There could be pizza, so don't start until the speaker is also.